Okay, so for our last probability lesson today, we're going to talk about something called independence, which we had mentioned earlier in the beginning of our probability unit. Two events are considered independent if their probabilities don't affect each other. Okay, so what we're going to do is we're going to look at when you have a two-way table, how do you determine if two events' probabilities are actually independent of each other? Does one affect the other? That's the idea. Okay, if they're independent, one will not affect the other. So I'm going to skip right ahead to the definition of independence in terms of probability. Two events are independent if knowing that one event occurred does not change the probability that the other event occurred. So a very easy example that I gave you the other day of independent would be if you flip a coin and you roll a die, what happens with the coin does not affect what happens with the die. That's what it means to be independent. We're now going to look at things that are a little more closely related and decide how do you know if they're actually independent of each other or not. So here's the formula we're going to follow. Two things are considered independent if the probability of A given B is the same of probability of A. So what does that actually mean? That means that the chance that event A happens out of everyone, or the chance that event A happens out of a specific group, if they come out to be the same, then it means that event B had no impact on event A. That's the idea behind this situation. Okay, so the way I like to talk about it in terms of formula, you're doing a given probability, and whatever your first letter was, the thing that was not the given, the thing you were trying to find out, if you test that probability by itself and they come out to be equal, that means that you have independent events. Okay, so using the table above, it says determine if having asthma and living in a house with at least one smoker are independent. Okay, so let's call these A and S just to make it a little simpler in terms of letters. So what we're going to do here is you're going to check that the probability of having asthma given you live in a house with a smoker would be equal to just the probability of having asthma by itself. If these two probabilities come out to be the same, then it doesn't matter if you live in the house with a smoker or you just are anywhere. If they're the same, that means these events are independent. I think you're probably going to already know in advance that these are probably not going to be independent just based on the nature of them, but I'm going to show it to you in probability form. Now, I will just say before I go and do this calculation, I can switch the order of the letters. I can make it probability of S given A. Okay, it doesn't have to be in any specific order, but I would then be checking against the probability of just S by itself, because of the fact that that's the very first letter in that given probability. Okay, so you always match up the first letter in the given with the probability by itself, and then you see what happens. So let's do probability of A given S. So you're going to go to this thing right here. This has no S, this is S, this is A, this is no A. Okay, so the first one we're doing is probability of A given S. So given S means you're going to focus just on this S column. Okay, so you're saying out of these 395 people, how many people had asthma? 113 out of 395. So you're going to do 113 out of 395. Okay, if I turn that into a decimal, that comes out to be 0.286. Okay, if the probability of having asthma just in general comes out to be 0.286, then these probabilities would be independent. If they're not equal, then they are not independent. So now I go back to my table and I'm doing the probability of just A by itself. Okay, so how many people were there that had A? 182. Out of how many people in total? 937. So when I check 182 divided by 937, that comes out to be 0.194. So you can see these probabilities are not equal, therefore it is not independent. Okay, these events are linked to each other. Living in a house with a smoker affects the chances of someone having asthma. Okay, these are not independent events. So, as I mentioned before, the letters can go in the opposite order. So again, the idea is match up whatever the first letter is as an individual probability when it comes to, choosing the letters out of the given. So just to recap again, probability of S given A. How would we handle that from this table? S given A. Given A means you're going to focus specifically on the A row. So out of those 182 people, how many people live in a house with a smoker? 113. So over here you're going to do 113 out of 182. And you're going to check that against just the chances of being a smoker. Okay, so if I erase this really quick, the chances of living with a smoker, one household member that smokes, 395 out of 937. So 395 out of 937. And when I do that calculation, I get 0.621. And on the right, 0.421. So you can see right here, not equal, not independent. Okay, so just to sum up what we're doing so far, when you're checking to see if two events are independent of each other, you take those two events and you make some sort of a given probability, and you set it equal to an individual probability. And if those two things come out to be equal, then these events would be independent. If they are not equal, they are not independent. So let's take a look at one where we have to actually set up the two-way table and then determine if they come out to be independent. So it says a credit card company, and this should be familiar to you because we used this one the other day, says that 42% of its customers are classified as long-term, 35% pay their bills in full every month, 23% are long-term cardholders who also pay their bills in full every month. Find out if these events are independent of each other. Okay, so I'm going to make a full two-way table just to recap it, although I don't necessarily need the full two-way table. I really just need the end probability and the totals for each individual event. So since the fact that we're dealing with percentages and percents are out of 100, I'm going to do a theoretical 100 sample table. Okay, so I'm going to have my theoretical, group of people that are surveyed 100. Remember, if it's 3 decimals, you do 1,000. If it's 2 decimals, you do 100. Technically, 42% is 0.42. Okay, so you decide what you want to put. So I'll put L and not L, and then F and not F. Okay, and I'll fill in the information provided. It says 42% of its customers are long-term. So 42 out of those theoretical 100 people are long-term. That leaves you with 58 that are not long-term. It says 35% pay their bill in full every month. So 35 for that, and then 65 would not pay their bill in full every month. And then it says that 23% do both. Okay, so 23. So technically, again, if I want to fill in the rest of the table, I would just take 42 minus 23, and I would find out this is 19, and 35 minus 23 and find out this is 12, and 65 minus 19 would give me this 46. But truthfully, all I really need to have is just the and probability and either one of these totals. Okay, that's eventually what I'm going to end up using. So what we're going to do to test to see if these events are independent is you're going to make a given probability and test it against a specific individual probability. So let me just start with this one. Probability of L given F. Okay, does someone is a long-term cardholder given they pay their bill in full every month? You are going to test that against the probability of just being a long-term cardholder. If these two values come out to be equal, then it means being a long-term cardholder has no impact on people who pay their bills in full every month or vice versa. Okay? So, probability of long-term cardholder given full-time pay in full every month. So, given means I'm going to focus specifically on the F row or column. So, out of these 35 people who are full-time who paid their bill in full every month, 23 of them were long-term cardholders. Okay, what are the chances of being a long-term cardholder in general? A long-term cardholder is 42 out of 100. Again, remember that we were given that in the beginning, 42%. And so I'm going to check these two decimals and see if they come out to be equal to each other. This comes out to be 0.657, and this comes out to be 0.420. Clearly not equal to each other, so therefore these are not independent. Okay, so what this is honestly telling you is saying 65% of people who pay their bill in full every month are long-term cardholders. People who are long-term cardholders, there's only 42%. There's a much higher chance that if you choose from the group of people who pay their bill in full every month, that those people are long-term cardholders. And again, these are all things that are eventually going to lead into statistics and data analysis and things like that if you were going to end up using something like this in the real world. I'm not going to go do the whole probability, but I do want you to know you could have done probability of F given L and tested that against the probability of F by itself. And again, you would see that those would not come out to be equal, so therefore it would still show you not independent. You don't have to do both, but I'm just saying you could do it either way and still get the same outcome. Okay, so let me skip ahead to this last example, number 4. It says the following is a hypothetical 1,000 two-way table representing the results of a survey where a selection of adults were surveyed to see if they watched an online advertisement about visiting New York and then their plans to visit New York within the next year. Okay, are the events a person watched an online ad? So you know we'll refer to that as watched. Okay, so the person watched and did not watch, and this person is vacationing, and this person is not vacationing. Okay, and it says that a person planned a vacation to New York, so we'll call that V. Okay, so we want to find out, are these events independent of each other? Did watching the online ad influence people to come visit New York or not? So you're going to do a given probability. So you decide the order. I'll do it in the order I see it right now. So probability of W given V, and I'm going to check that against the probability of just W by itself. Again, the idea is the chance of picking someone who watched the online ad the same whether I pick from everyone or I pick from the people who are vacationing to New York? If they come out to be equal, then these two things would not affect each other. So probability of W given V. Okay, so my given is V, so I go to my V row or column. So out of those 400 people, how many watched the ad? That would be 300 out of those 400 people. What are the chances that someone watched the ad in general? That's 750 out of 1,000. So you can see either way, these both come out to be 0.75. So it doesn't matter if I'm choosing specifically from the group of people who are vacationing or I'm choosing from everyone, the chances of getting W are the same no matter what. So therefore, these events are independent of each other. Okay, the chances of one do not affect the chances of the other. So I do want to point out, you could have also done V given W and check that against the probability of V by itself. Again, you would see that those would still come out to be equal, so you would still get independent. You don't have to do both, but I'm just showing you that you could do it, again, in different ways and get the same outcome. So just to recap really quickly, in the last two examples, and you can go ahead and try these ones in your workbook, but if I wanted to check to see if ripe and bruised were independent when it comes to these avocados, I would set up a given probability, ripe given bruised, and I would check that against the probability of ripe by itself. Again, you always want those first letters to match up with the individual probability that you're checking. Or you could do probability of bruised given ripe and see if that's equal to the probability of being bruised. And again, not equal, not independent.